extinction possibility, although it's often sold as being so. Yes, the world is going to get a few degrees warmer, which we will learn to live with. All right, and that's part of the discussion towards the end of the chapter. It seems kind of depressing to look at the climate records, what's happening with the acidification of the oceans, sea level rise, which amazingly hasn't risen all that much, and so on. All right, but certainly climate change is a very important science, environmental science, and maybe even a cultural issue too, because issues in climate change may influence what kind of car you drive, how much you pay in taxes, how much you spend on fossil fuel utilities, and so forth. All right, what are you looking at here? You're looking at the melting Arctic ice. That's just for one season. You know, that's not climate change. That's just showing how the ice expands and contracts over the year. The issue, though, is that when you look at the overall average, the extent isn't so much, and then the length of its furthest extent isn't so much either. And so now there's open waterway across the Arctic Ocean in some years. Well, no doubt about it, though, most of the world's glaciers are melting back. Some of them have surged, but overall, the vast majority are in a retreat. Here's a couple pictures from the ebook that shows glaciers. And when an iceberg drops into the sea, there's a term for that. It's called calving. All right, now you're too young to remember the famous cartoonist Gary Larson. He had his series of hysterical cartoons in his series called The Far Side. And with this one, I see a couple things, though. One, he made this before the asteroid impact theory became accepted. Back when I was growing up, and I read probably every dinosaur book there possibly was, is that they told us, well, that the dinosaurs couldn't adjust, they were too dumb, and then climate slowly changed and the mammals took over. That's not accurate. And well, anyways, that's a whole other argument. But certainly, we're not like the dinosaurs. We have a great capacity to understand and adapt to a changing environment. Well, is the words climate change actually an oxymoron? Like jumbo shrimp, or I don't know, some of these other ones are kind of snarky, business ethics, meaning there's no ethics in business, or military intelligence because of right, or civil war. Yeah, how can you be civil and be in a war? All right, so it seems to be a term that contradicts itself, especially at the beginning of the course when I told you the difference between weather and climate. You know, weather, state of the atmosphere at any one particular time and place, and it's always changing. Whereas a climate description, that's the average, that's the usual, the range of expectations. So that's not supposed to change. That's what you compare everyday weather to. But certainly climate does change. The world that we live in is a lot different than the world that the dinosaurs lived in. Here's a photograph of Pembroke 66 million years ago. And I think it's late April. It might be a Tuesday, though, about 3 o'clock. And then over here, this is Pembroke 20,000 years ago, still during the Ice Age. Was Pembroke covered by a glacier? No, it wasn't directly glaciated. But environments in Pembroke at that time would be like environments in the high Arctic close to the glaciers, what we call a periglacial environment. All right, well, so that's So over millions of years, so over thousands of years, climate obviously changes. But can climate change over a human lifespan? Indeed, it can. If you wanted to find a climate average as a 30-year average, well, even over a human lifespan, you can get wetter or drier. I believe last time when I was looking at some slides of the Dust Bowl, certainly the climate of the Great Plains changed significantly over the course of the 20th century, back and forth for the wetter and the drier. All right, so yes, climate can change over a human lifetime. All right, now there's also a little bit of recap of the climate system. Some of this we got in chapter 1. We have right, the atmosphere, the hydrosphere, the biosphere, and the geosphere. They're adding in another sphere here, and that's the cryosphere. Despite it's the word, that sphere isn't all the tears of human suffering. Cryosphere means ice or frozen. Sometimes you hear the word cryo in another context of cryonics, meaning freezing things and how they bounce back. So the cryosphere is all the ice in the world, and it overlaps those other spheres too. All right, so the 5 major parts of the climate system. You can see the atmosphere, that's the air, and the clouds are up in there, although the clouds are part of the hydrosphere. You see the water, that's the hydrosphere. You see ice up in the mountains, that's the cryosphere. All right, so the cryosphere, I might say that's technically one part of the hydrosphere, although sometimes it acts like a surface, like the geosphere. All right, so studying the interactions of all of those is part of Earth system science. All right, so here's the cryosphere. This is a view of the last glaciation during the last ice age, and there have been many ice ages. Was Pembroke directly covered? No, but look where the glacier is. Look where North Carolina is. So we're fairly close to it. So environments at that time were like what you find up in the high Arctic today. And also, it would be way off the topic, and I'm tempted to talk about it, but also the formation of the famous Carolina Bays, the mysterious Carolina Bays, were likely formed during the Ice Age. But that's a whole other topic. And so, how has Pleistocene glaciation shaped and influenced our world? When we say Pleistocene, that's more or less synonymous with the Ice Age, but capital V. The Ice Age, the last Ice Age, was the Pleistocene. Well, it has a lot of effects in the world, not only the changing of the climates, but when you have a lot of the world's water that's in the form of ice sitting on the continents, that changes sea level. Also, those big sheets of ice, as they spread out under their own weight, they sculpt the environment, gouge out depressions, gouge out the Great Lakes, and also deposit debris, sands and silts, and other drift, sometimes boulders. All right, this is more something that you would study in physical geography or earth science, but certainly glaciers are always moving. They're like a conveyor belt, and it's shown in the animation there. You can have a melting glacier, but still the movement is all forward. It's carrying that debris with it. It's a very important erosional agent. For a long time, it was a secret agent. It took us until the mid-1800s to figure out how glaciers could sculpt the landscape. Back before that, I thought that all these landscape changes and boulders that were plucked out of one layer of rock in the Arctic and deposited in North Carolina, I thought, well, they came down in Noah's flood. That's how they got here. All right, so here's a sequence animation. So you have the glacier filling up the valley, carving V-shaped valleys into U-shaped valleys, and when those are filled in with water, those are fjords. And continental glaciation. I went to Kent State University, and the campus was a living laboratory of glacial features. And sometimes we would even talk to each other and give directions based on the glacial features. Where I would, somebody was asking me, well, where's Satterfield Hall? And I'd say, well, follow the Esker down to the Kame and make a right at the Drumlin, and it's right there. So we were all glacial geomorphologists there. All right, so a big bulldozer. Does it surprise you why Hudson Bay is a big embayment? That was the center of the ice sheet that weighed down the landscape. It's slowly rebounding up now that ice has been removed. All right. All right, so as I go around the classroom asking you, can you explain one part of these or another? How do changes in type and amount of cloud cover affect climate? Well, clouds reflect, but then clouds also absorb Earth heat too. And so there's that albedo effect and the absorption effect. How about changes in the amount of sea ice? Well, if there's a lot of sea ice, there's a higher albedo, more reflection, climate's cooler. But if the sea ice melts back, you get more absorption of solar energy, and you have a warming water, which means more sea ice will melt. So climatologists have to study various feedbacks involved here. All right. Some of this is involved in physical geography and geology, looking at the weathering of rock, taking carbon dioxide out of the atmosphere, volcanism, putting it back in. All right. Well, whenever you talk about climate change, you have to bring in a little bit of the messy geologic timescale chart. What era are we living in right now? All right, so in the last one, we're living in the Cenozoic era. So where's all the dinosaurs? Oh, well, that's the Mesozoic. This mark marks the extinction of the dinosaurs, the asteroid impact, and then all of these are inventions of the human mind. Okay, this is what we call them. All right, so we live in the Cenozoic, and then you divide it up into periods, and we're living in the Quaternary period, and then the epoch. It took an epoch to do it. We're living in what's called the Holocene. What's the epoch just before us? That's the Pleistocene. That's what we call the Ice Age. But during this period, there were a number of ice ages as well. You'd have to say that in the past few million years, there's been several glaciations, meltback, when the environment is just like what it is today, and then the glaciers build up and flow again. This has happened 24 times in the past 2.5 million years. So how do we know that the ice age is over? How do we know we're not just in another interglacial? Well, because it says right here on the chart, we're not in the Pleistocene anymore. We're in the Holocene. That's an invention of the human mind. A lot of books talk about an Anthropocene, which would probably start about 1950 or the nuclear age, post-World II age, when there was a lot of industrial development around the world, right? You could mark it in layers of ice or rock with the radiation from the fallout of the atmosphere. What they call the new man epoch. So that's the epoch where we've influenced practically everything in the Earth system. It's the Anthropocene. All right, it's not in our book though. They say Holocene. So the answer to the question of which epoch we're in right now, we're in the Holocene. What else? What if you look at the past 65 million years of the Cenozoic. The world the dinosaurs lived in was a lot more tropical than the world that we live in. So we're still in the ice house. But, you could very well justify that we're still in the ice age right now. I think in that video clip I showed before class, he said it. We're still in an ice age. So climate changes up and down in temperature. We're concerned about that, but overall, it's been getting colder. We're still on the ice house side of the Cenozoic. Isn't that a brand of beer? Ice House. Sounds familiar. We're still in the ice house. All right. Well, so how do we know some of these things? If you want to be a scientist and you want to study climate change, well, the measured temperature record isn't all that long. So we have to use something called a proxy. All right, someone that's going to be the substitution in some way. Here, it's a proxy vote. I'll vote for you, since the real senator can't be there. I'll put in a proxy vote. All right, so it's proxy data. Well, it's data about climate, temperature, and conditions based on something else. And we have several slides on seafloor sediments, glacial ice, fossil pollen, tree ring growth, historical documents. Human memory, how far back can that go? All right, so there's an entire field of study called paleoclimatology, who try to piece together ancient climates in Earth history. Dr. Farley, who's chairman of the Geology and Geography Department, he's a paleophylanologist. He studies ancient pollen in order to assess past climate change as part of an understanding of geology. You didn't know you could do that. Okay. Now, well, tree rings is one of the methods. Human lifetime is maybe about 100 years if you're lucky. Here, this bristlecone pine is 4,000 years old. So it was alive at the time. It was alive before Christ. It's seen the lifetime of Christ. It's seen the rise and fall of the Roman Empire and many other empires, the American Revolution, World War II. It's seen all of that. Its tree rings are a record. Its growth rings are a record of past environmental conditions at that point. So yeah. Glacial ice. Well, scientists go to the Greenland and Antarctic ice sheets and take cores of the glacial ice and sample them. And they look at the little bubbles that are trapped in the various layers. And they say something about the ancient atmosphere. It tells you things like the carbon dioxide, the greenhouse gas, the particulates. In the H2O ice, what kind of O it is, which isotope of oxygen is more prevalent in one layer or another. So you use that proxy data and match it up to other proxy data and other known things to see what average temperatures may have been like. All right, now this graph is a graph of the carbon dioxide content. Carbon dioxide goes up and down and up and down. It doesn't exactly match the temperature record, but it's close enough. But it's been unprecedented since the end of the Holocene, since the end of the Ice Age, or the beginning of the Anthropocene, that carbon dioxide has gone straight up. All right, so all kinds of things can be gotten from this glacial ice. It's recording everything. It's recorded the nuclear tests in the 1950s and 60s. Various volcanic eruptions. There's a little bit of the dust on every one of those as well. So a lot can be understood by looking at the glacial ice. And then the forams. That's what they call them. Foraminifera. Everybody says forams. All right. Well, in the seafloor sediment, you can also take cores, right? So you're looking at sediment, you're coring down into these old layers. Well, the ancient shelled organisms can tell you a lot because some species thrive in warm oceans, some species thrive in cold oceans, and also in their shells. Uh, there is oxygen atoms as far as their calcium carbonate of their shells. Well, how much of the oxygen isotope that's associated with warmer or colder periods is in that? So those layers can be studied, and you can figure out if it was climatically a glacial period or not. All right. I think Dr. Farley's also, he knows quite a bit about the forams too. He teaches a course in Earth history, which I can recommend to you. As well as he has the dinosaurs class, but that's off the topic. Well, let me ask you this. If you buy a newspaper every day and you pile one on top of the other, which paper is the oldest one and which one is the most recent? Well, that's kind of the principle of looking at the glacial cores and the seafloor sediment cores. You look at these as a sequence in layers and you see what's there. Okay, here's the vessel that's a big plunge that's going to take very deep into the seafloor. Because first you have to go through the sea, and then you hit the bottom, and then you have to core it out. So you need some deep drills for that. All right. Similarly, as I said, scientists collect these cores and the ice layers. When these are studied and compared and coordinated, then you can then estimate by proxy what conditions were like hundreds of thousands of years ago. They're making sure they don't get snot on the ice core because that would contaminate it. All right. So oxygen isotope analysis. All right. Now, in chemistry, you learned all about isotopes, so I don't have to explain it, right? So it's a special form of oxygen that that has more neutrons. So the regular oxygen is O16. All right, but you have a certain amount of O18 isotope as well. It's heavier. All right, and so the O16 is lighter, it evaporates more readily. So if you have more O18 isotope in the seawater, in the shelled organisms, and then in the sediments, that means that's glacial times. And then more O16 in the interglacial times. I think the quiz question asked you that, so that's the reason why the answer is pulsing there. Okay. Okay. Does that make sense? Isotropically light, H2O. So that has more of the O16. All right. And similarly, because there's oxygen in the calcium carbonate of the forams, other shelled organisms, you look at how much O18 is in there. Okay. So if there's more O18, then that layer indicates the glacial period. So this is good, dependably, for at least 100,000 years. Okay. Well, let's see. I like in the new book, they, instead of putting the O18, O16 ratio on this axis, they actually told you what that is in temperature here. It makes it, it's the same graph, but it's a lot easier to read. I don't know if on the homeworks they show you this one, but it has the ratio here. Well, then you have to juggle that. Okay, well, what does the ratio mean? Which one's warmer or colder? It's easier just to write the temperatures on here. Okay, so colder, warmer. All right. And also something about this graph, how do you read it? Don't you usually look at the end of the graph? Right? But that's 40,000 years before present. Well, how many years is it right now before present? 0, because we're present, right? So we're down on the end of the graph, or depending on when the graph was made. So here, well, what do you see? Uh, what do you see? You see some ups and downs. There's some glacial, interglacial periods here, weren't there? As this one, no, okay. This one, 15,000 years ago, quite a bit warmer. And then all of a sudden, you get a lot colder. Earth scientists are still having fistfights over why that is. That slide might come up later. Yeah, it's the Younger Dryas period. And then steady warming after that. And so here we are, the past few. So that's saw the rise of civilization, past few thousand, the rise of human languages as well. And so here we are, a lot warmer than during the Ice Age. Well, even during the Ice Age, you had your ups and downs. You had some fairly warm interglacials. That's what the Greenland ice core data shows. Oh, yeah, I don't know. How much of this should I talk about? Because you can sometimes climatologists get in fistfights and they start rolling out into the street when they discuss what happened during the Younger Dryas. Well, just when things were warming up, I thought the end of the Ice Age, then things got suddenly colder for some unknown reason. And it also it correlates with the end of the megafauna, which may have had something to do with the rise of humanity in Eurasia and North America, disappearance of it. Also, a big decline in the native people's technologies of what they had. They had much better arrowheads before the Younger Dryas kind of set civilization back a little bit, even though it's still Neolithic. What happened? And also the Carolina Bays, they dated back, many of them date back to this time. Something happened. Was it a big impact? What happened exactly? Well, yeah, that hypothesis is very controversial. That's what I mean by they're having fistfights. They shouldn't have fistfights, but people have very strong opinions on this type of thing. Younger Dryas. Dryas is a type of flower that grows in the Arctic. All right, tree rings as a proxy. Well, how does it work? Probably a lot of you probably knew this already. You might have had this in science, talking about tree rings. Here you take a core of the tree. You don't have to kill the tree. If you take a core, yeah, if you cut it down, make it a big slice, you could read it that way. But you can also take a core through it, so you don't have to kill the tree. Well, the trees thrive when it's warmer and wetter. Usually it's wetter that's been looked for. This has been used to study climate change, especially in the arid portions of the country. There are dozens, hundreds, thousands of science papers on tree ring research in the Southwest. Many PhDs were made from that. So it's an important part of climate change, right? So the quiz question probably asks you this, right? Is it thick rings or thin rings? Thick rings are favorable conditions, usually more moisture. Right. Oh, and that's what I said. Here's the bristlecone pine. I don't think I would want to cut one of those down. It's 4,000 years old. So that's a best. Most tree ring research doesn't go back that far. It's also an important part of calibration with other proxies is the tree ring data. Pollen? Why would anybody want to study pond scum? Well, if you've got layers of it, it tells you what used to grow there. And so if you have species of trees that don't grow in this hot of an environment, they grow in the Arctic, that tells you that the environment used to be a lot different. All right, and so this is what a phylonologist would do, is study the ancient pollen. Much the same way, corals can also be studied, the composition of them, where they are. What if you have a coral reef that's very far inland? Well, then the sea level must have been up there at one time. And also you can study these with oxygen isotope analysis as well to try to figure out what the temperature of the ancient seas were like. Historical records, yes, there is evidence, and this may fill in some gaps or maybe verify things, and for things like ancient storms and that type of thing. The ship's logs, because what's there to do at sea? Watch the sky, take measurements, map the coastlines, right? So that can tell you about conditions. Jesuit priests were good at collecting information. Old newspapers, but then are they trustworthy? There's a lot of gaps in those. You know what's good for studying grain harvests in Europe or the climate of Europe? A lot can be done by looking at the price of rye in Europe, which goes up and down depending on how much rye there was. And it tells you climatically what kind of year it was. And you know who takes very good records is medieval monks, because, well, what else do they have to do except sit in their cells and copy the Bible and pray? Well, they also have produced a lot of wine too. And you might know this because North Carolina is a age 21 state, and you're not old enough to drink alcohol yet. But someday, if you drink responsibly, you may drink wine. Winemakers take the physical environment very, very seriously. They take things like climate, degree days and such very, very seriously. And so there's intricate records of that. Well, what about the measured record? Remember chapter 3 and the measured record, the max man? How far does that go back? Well, 100 years here, 150 years there in our network of stations. But these are also good because these are a good way of calibrating the tree rings and the pollens and so forth, so that these are in agreement. And the temperature curve takes more and more of an honest shape as long as you cross-reference these things. All right. We've seen this before. Okay. Well, what about human memory? Back when I was in elementary school, I had to walk a mile to school through 3 feet of snow on occasion. It's uphill on the way there. It was downhill on the way back. Human memory can be a little fuzzy, though, but I will tell you that the 60s and 70s were a snowy period. And it was a time of a little bit of global cooling. Back in the 60s and 70s, teachers and professors didn't try to scare students with the threat of global warming and human extinction. Back then, they tried to scare students with the threat of another ice age and human extinction. All right, we'll be fighting over coats. didn't happen. All right, so human memory, a lifetime, and again, for filling in gaps, the historical record is okay. All right, so and some of this. Oh, the Dust Bowl. I talked about this in looking at human accentuated air pollution. The Dust Bowl, certainly that was a period of climate change. In the early 1900s, it was a lot wetter out there, and there was a big demand for wheat in Europe. So of course, farmers went out there and got rich by planting wheat. And also, isn't it true that rain follows the plow? Yeah, the plains are semi-arid, but if you go out and farm it, it makes it wetter, doesn't it? No, of course not. That was a big mistake, because what they did was they plowed up a lot of land that shouldn't have been plowed up. And when the climate changed back to normal, then they all lost their livelihoods, turned into a dust bowl, crop failure here or there, out migration, and so forth. Many harrowing tales in the study of climate change within a human lifetime, and that's the Dust Bowl. Okay, the concept check questions. What are proxy data? Well, records of past climates that come from other sources, not direct temperature measurements. It's necessary because direct thermometer measurements only go back responsibly about 150 years. Okay. Well, what causes climate change? Are human beings responsible for climate change? Can contribute to it. But what about before there were humans? The climate's changed. What kinds of changes? In short, this list, which I have a couple slides on each one of them. All right. Plate tectonics. Why are there glaciers in Africa? This was in the Hitchhiker's Guide to the Galaxy, and the guy was creating the glaciers of Africa. Now you've got glaciers in Africa. How could you possibly have glaciers in Africa? Well, at one time, it was at the South Pole, so it was covered by an ice sheet. This is every Earth Science book shows the breakup of Pangea. This is the most recent breakup. There were other breakups. Also, they all collided together, and then they all broke apart. They all collided together here. So you have the drifting of the continent. So in India, yeah, you can find evidence of glacial features, glacial erosion and deposition in India. Okay. Yeah, it was a tropical swamp here at one time. Well, can plate tectonics help us understand it? Yes, because you have to have ice sheets in the high latitudes in order to get the ice to build up on them. But the plate tectonics then can show us evidence of the ancient ice ages, but not short-term climate changes. And not the recent ice age, although the positioning of the continents and the connection of North and South America and the height of the Himalayas, yes, those are all factors. But if you're talking about the ice age going back 20,000 years, it takes tens of millions of years to get the continents to move around. So that picture, well, let me see, go back a slide. Right? See this one here. This is today. Well, what was it like 20,000 years ago? Pretty much like that. Although, yeah, the glaciers are on the continents, the sea levels were lower, but the position of the continents wasn't changed that much, because it takes tens of millions of years to move. So plate tectonics certainly does help us understand long-term climate change, not short-term, is the answer to that quiz question. Oh yeah, another change. It's amazing that this was worked out. Milutin Milankovic was a Yugoslavian Serbian scientist mathematician that worked without a calculator. I can make the story very, very long, but will it become that much more interesting? He was in prison for choosing the wrong side during World War I, Serbia. So in his prison cell, he worked out the orbital variations of Earth that explain long-term climate change without a calculator. All right, so he looked at changes in the shape of the Earth's orbit, the tilt of the axis, and how much the pole points in different directions. All right, let's take a look. There are several textbook, ebook slides that show this, and I have this in detail. There's also a very good link in your ebook and homework questions to one of the smart figures that looks at that. All right, well, let's see. Overall, I'll give you the conclusion here first before I explain it. I want the conclusion so that you should learn this. What you want to do is you want to adjust the orbital variations so that you have milder winters.